What if I told you that the classic board game Snake and Ladders is actually a coding challenge in disguise? That's right, today we are solving a super fun algorithmic problem where the board is a matrix, the dice rolls are random moves, and the snake and ladder decides your fate. But here's the twist, we'll calculate the fewest dice rolls required to win the game using C sharp. Let's jump on it. Alright, here's the problem. You're given an n by n matrix representing a snake and ladder board. The cells are numbered in a zigzag pattern starting from bottom left corner and snacking back forward until the top right. Your goal, reach the final square in as few moves as possible. Sounds simple, right? But here's the twist. If you land on a square with a snake or ladder, you're automatically moved to its destination. And just like rolling a die, you can only move up to 6 steps at a time. So how do you calculate the fastest path to the finish line? I remember tackling this problem for the first time and it felt like playing an actual game of snakes and ladders. Every decision on dice roll was critical just like in real life when you're strategizing the next move. But here's the cool part. Once I structured the problem into a graph traversal algorithm, it all started to click. I'll show you exactly how. Let's start with the flatten board function. This method takes a 2D board matrix and converts it into a 1D array for easier processing. Here's how it works. We first get the size of the board since it's an n by n matrix and represents the number of rows and columns. Next, we calculate an array called flatten to store all the elements of the board in a single dimension. The size of this array is n by n, which is the total number of cells on the board. We initialize two variables, index to track the current position in the flattened array, and direction to control whether we traverse a row left to right or right to left. We loop through the rows of the board starting from the bottom n-1 and moving upward to the top, that is row 0. This matches the numbering on the snakes and ladder board. If the current direction is left to right, that is direction equal to 1, we loop through all columns in the row from 0 to n-1 and add the values to the flattened array. If the direction is right to left, we reverse the column traversal going from n-1 down to 0 and add the value to the flattened array. And at the end of each row, we flip the direction by multiplying it by -1. This ensures the zigzag pattern of traversal. Finally, we return the flattened array. This makes the board much easier to handle for the rest of the algorithm. Now, in the snake and ladders functions, we again get the size of the board and call flattened board to convert the matrix into a 1D array. We create a visited array to keep track of which cell we have already processed and a queue to implement breadth first search. Each queue entry is a tuple containing the current position and the number of moves taken so far. To start the BFS, we enqueue the starting position square 1 represented as index 0 and we also mark it as visited. Now we enter the BFS loop. As long as there are nodes to explore in the queue, we keep processing the queue in the next element in the queue, which gives us the current position and the number of moves we have taken so far. We simulate rolling a die by iterating through all possible outcomes, that is 1 to 6. This represents moving between 1 and 6 squares ahead. We calculate the next position after the dice roll. If the position goes beyond the board's last square, we stop processing further rolls. We check if the square has the snake or a ladder. If it does, flatten next is not equal to -1. We update the destination to the target square of the snake or a ladder. Otherwise, the destination remains the same. If we haven't already visited the destination square, we continue processing it. If the destination is the last square on the board, we immediately return the number of moves required to reach it. Otherwise, we mark the destination as visited and enqueue it with the updated move count. And there you have it, a perfect algorithmic solution to a classic game By flattening the board and using BFS, we not only made the problem manageable but also guaranteed the shortest path. This approach is efficient, elegant, and also ready for any coding interviews. And now it's your turn to try it out on different board sizes and let me know how it works for you. If you have enjoyed this breakdown, smash that like button for more awesome coding content and share your thoughts in the comment below. Until next time, keep coding, keep learning, keep winning just like on this board.